Okay. Okay, hopefully now everything should be working fine. My name is Valerio Carruba, and I'm a professor at São Paulo State University in Brazil. So my main interests have been discussed on astrodynamics, secular dynamics of asteroids, etc. But in the last 3 years, I've been trying to applying machine learning methods to study classification of asteroid orbits and similar problems. So I'm very grateful to the organizer of this conference, Professor Ugo Locatelli, Dr. Christoph Lotka, Professor Anna Selletti, for inviting me to this talk and giving me a possibility to talk about the recent works we have been doing here in Brazil. So why machine learning is important? Machine learning is already present in our daily life. So it's used currently for automatic image recognitions on the streets, for translating tests on Google Translator, for example, or for automatically selecting through deep learning the videos on YouTube. This is done by a deep learning algorithm that studied your previous past history on the site. It has application on medicine. It's used to diagnose some kind of tumors using tomography of brains and studying the shape of the tomography with respect to known diseases and similar other applications. So in the previous talk, machine learning is discussed at length. So it's a subfield of engineering computer science. Machine learning explores the study and construction of algorithms that can learn from their mistakes and makes prediction about the data. So there are 3 major categories of machine learning. We can have supervised learning if the computer is presented with an ensemble of entries. The goal is to learn a general rule that maps inputs to outputs. Unsupervised learning, when no label is given to the learning algorithm, leaving you alone to find the structure of its entrance. This is essentially clustering or anomaly detection. And reinforcement learning, where a computer program interacts with a dynamic environment. As it navigates the problem space, the program receives a return similar to the rewards, which it tries to maximize. Most applications of reinforcement learning are, for instance, about cars that are driving themselves. And I'm not going to talk much about this kind of class of machine learning. So 3 years ago, we started to look into this branch of computer engineering, and we found that there's a research group here in Brazil. MASB means a machine learning applied to small body, which has the goal to explore machine learning to study the dynamics of small bodies in the solar system. It's a collaboration between 3 institutions in Brazil and Peru by myself, Professor Rita Cassia-Domingos, William Barletta at UNESP, Dr. Safwan Al-Jibbai at IMP, and Professor Mariela Uaman at Universidad Tecnológica in Lima, Peru. All data that we obtain abides by the FAIR policy of data usage, which means that data should be findable, accessible, interoperable, and reusable, which means essentially in practice that all the code that we develop for our works, all the data is available on GitHub and is listed on the MASB site. So going back to machine learning, very briefly, we can discuss about some algorithms of supervised learning. Supervised learning algorithms have been developed in Python in recent years. They are available for free to the scientific community through the scikit-learn package by Pedregosa et al. 2011. Given a persisting population, this method uses the known data to predict whether the new data belongs to a particular group or not. Essentially, in the picture, you can see that the algorithm will automatically detect if the fruit is a banana or ripe. So we can define a standalone and ensemble method. Standalone method are methods that use a single algorithm. It could be decision tree, linear regression, as we're going to see in a few minutes. Or while ensemble method use several autonomous algorithms to obtain a result. We can distinguish between bootstrap aggregation or bugging, where training data is fair divided into several samples called bootstrap samples. Each model is counted with the same weight. And boosting, which emphasizes the training cases where the previous models made mistakes in the classification and the autonomous models that had the better performance. So the weights are different depending on the performance of previous methods. So let's talk about standalone methods. So the most common use, one of the most common use is linear regression, which looks for a linear relationship between an independent variable x or the input and a dependent variable y or the output. The algorithm uses the data from training sample and then calculate a probability for objects in the standard database of belonging to a studied group. The object is considered a member of the group if its calculated probability is greater than a limit value, which is a free parameter. So in this case, you have a vertical line which shows the 85% of the level. If an object has a value above this level, it will be considered to belong to this group and not otherwise. We can have one of the most common methods, which are the decision tree. Imagine when you want to decide whether you can use a kite. You need the weather to be windy, sunny, with low humidity. So every time you have to make a decision. You have to see if the weather is windy or not, if the outlook is sunny, overcast, or rainy, and if the humidity is optimal or not. So every time you make a decision, you have a branch in the tree. The maximum depth is a free parameter, one of the free parameters of the decision tree. You can have several branches, more or less branches, depending on the type of problem you're studying. As with Bayesian classifier, randomized forest, this is an ensemble Bayesian, STA3 is an ensemble method. You can combine different decision trees to obtain better results. And one example of this is the randomized forest method. So extremely randomized tree or STA3 sample data without substitution, which is a difference with respect to randomized forest. Decision of status of a data is made by majority of votes of the result of each autonomous model. So this is a Bayesian classifier method. You can have a boosting method. Examples are AdaBoost, GBoost, or extreme gradient boosting. The reinforcement algorithm track the model that provided the least accurate forecast and give them lesser weights. The final result is achieved as a weighted average of the result of each autonomous model. So the difference with previous method is that each model has given a weighted average, a weight on the average. So not all models have the same count. So in unsupervised learning, you can have application to small body mostly on classifying. So one example of supervised learning is KNN, or the basic idea is to predict the state of a point based on its closest neighbor. If most of the closest neighbors belong to a class, the point is also classified as such. So here, for instance, you have the star and you have 3 points that are closer to the star. The majority of these points is yellow, so this point will be given a yellow status. But this status depends also on the number of neighbors used for classification. If you use a larger value of k, for instance 5, then the majority here will be blue dots. And you will have a different classification for the model. So this is like many methods in machine learning, KNN depends on free parameter. Here is the free parameter is the number of neighbors used for classification. You have hierarchical clustering methods, which is the most common method used for identifying members of asteroid families. Very briefly, first it checks for objects closer to a parent body, then a distance cast. And if a new object is found, the new body is used as the parent body, the process is repeated until no new members are identified. So you can produce dendrograms. Here, each of the horizontal line represents the merging of two clusters, and vertical line represents different clusters. Once you increase the distance, the gradient distance, there can be a metric defined by the user. At some point, you will find a distance where all the points belong to the same clusters, and this represents the highest horizontal line in this plot. So these are some of the simplest algorithms in machine learning, and since our goal was to study application to asteroids, we would like to review what has been done in the past few years. So one of the first papers to apply these methods to asteroid classification has been Smirnov and Markov in 2017, which applied k-nearest neighbors decision tree, gradient boosting, and logistic regression to identify resonant three-body asteroid in the main belt. So you can have, we will see this more in detail later on in this talk, you can have 3 kinds of orbits for three-body asteroids, in three-body resonance. You can have asteroids that are circulating, the resonant argument essentially goes from 0 to 60 degrees, librating, the asteroids oscillate, the resonant argument oscillates around a stable point, or they can switch between circulation and oscillation. So the result of identification by machine learning method were accurate and take much less time than numerical integration. So you can actually train these methods on the orbits and classify the methods in questions of seconds instead of a few hours. So the authors identify 404 new asteroids in the 4-to-1 three-body resonance using these machine learning methods. Similar method can be used for classification of Kuiper belt objects. So there is a recent paper by Mulven and Volk in 2020 that use a GBoost model to classify KBOs into 4 dynamical classes. The KBOs can be defined into resonant population if they are in resonant motion resonance with Neptune, classical populations, which is this blue dot here, which are found at lower eccentricities, detached population, which are the objects that are scattered by close encounter with Neptune, and on the scattering objects, which are the objects that could not have been scattered currently by Neptune. So there are models that can automatically classify your newly discovered KBO into these classes, and it is useful to have at least a rough idea of what the dynamical behavior of the new KBO is. We can use a clustering method to identify a fission group within asteroid collisional families. Some families of asteroids may also be the result of spin-up induced fission of parent body in critical rotation. So in at least 4 groups of young fission, more than 5% of its members belong to subfamilies, and K-mean can be used to automatically identify groups in these young rotational families. Here you have an example of a rotational family that has 2 groups. The main family, then a secondary event was occurred after the formation of the main family here. So these are the centroid of these 2 groups identified by red stars here. Of course, you can use machine learning hierarchical clustering algorithms, which are different than the classical hierarchical clustering algorithm, to identify members of asteroid families. Here you have a limitation, essentially, because you cannot use this method in regions where the number density of asteroids is too high, because otherwise you will not be able to distinguish between nearby asteroid families. But in low number density of region of asteroids, like the high inclined regions of the main belt, this approach is found that is able to find family members with scores above 89.5%. So we identified 6 new family and 13 new clustering regions where the method can be applied 2 years ago. For families, the asteroid families that are in very high number density regions, you can still apply machine learning, but in this case, you can apply the also supervised learning method. So you can use non-asteroid families to to train the model and check for the distribution of new objects based on the distribution in proper element by non-family members. So we can compare the result of 9 classification algorithms for autonomous and joint approaches. And in 2020, we found that the extremely randomized trees or extra tree method had the highest precision, allowing to recover up to 97% of the family member identified with standard ACM method. So it is a really simple, relatively simple method. It's not deep learning, but still we are able to use it with some success. And finally, as discussed by Professor Dr. Lotk, one problem of machine learning method is the optimization of the free parameter or the hyperparameter optimization. You can have a method that depend on vast phase space of free parameters, and optimize each single parameter can be a very difficult task or time-consuming task. So you can use what is called genetic algorithm to perform this parameter optimization automatically. These were introduced in 2004 by Peng Wei, and essentially they works like genetic evolution in the biological system. You start with a few models, and you select the best performing model among your sample over a generation. Once you select the best models, you change the parameter in the best model, you let it evolve once more for a few generations. You get at least one best performing method. So you are not guaranteed that you get the best possible performing method, but you will get one of the best among the methods that are possible for your problem. And we have recently used this method to select the ideal algorithm fitting the asteroid population in the secular resonance Z1 and Z2. And you can see in the bottom panel the population of vibrating asteroids as predicted by the method. And this is very close to the one that are confirmed by numerical simulation. So this is just the genetic algorithm may be useful for this kind of problem. So these are some of the simplest methods that have been used in celestial mechanics recently. Dr. Rodriguez talked about time series and deep learning, and the second part of my talk will be mostly about exploring some application of these methods. So one of the applications could be for chaos detection. Chaos in the dynamical system can be identified using an approach based on the autocorrelation function of time series, the ACF index or ACF phi. So what is autocorrelation? We can compute the correlation coefficients between two time series, and they tell us how strong two time series are related. They are defined as the ratio of the covariance of the time series with respect to the product of the standard deviation of series X, the standard deviation of series Y. If R is equal to 1, we have strong correlation between the two time series. For R equals 0, the series are not correlated. For R equal -1, the series are anti-correlated. And so the values of R are between -1 and 1. So we can define autocorrelation function using autocorrelation, determine the autocorrelation coefficient of time series with respect to lag copies of the time series itself. So we can define a Y series with a lag 1. This will be just X1, Xi -1, with lag 2, Xy -2, and so on and so forth. So the autocorrelation function is the spectrum of autocorrelation coefficients for various values of the time lag. So for a periodic function like the sinusoid, all autocorrelation coefficients are equal to 1. So it is always possible to predict the future behavior. But for a series like the white noise, which are essentially random variable with constant mean and constant standard deviation, all autocorrelation coefficients except the first one, of course, are 0. So it's not possible to predict at all future behavior of this time series. So we can define a chaos indicator based on the autocorrelation function, and we call this autocorrelation indicator the ACF, which is defined by the formula that you see in the screen. This is the fraction of the autocorrelation coefficient that are larger than 0.05 in absolute value. And 0.05 is the null hypothesis for autocorrelations in autocorrelation theory. In a time interval defined by between I final and I initial. Why this time interval? We don't want to go close to 0 to have a short time correlation factors. So you can see two examples of autocorrelation function. You can see one for a regular orbit in the region of the Veritas families, sorry, where the autocorrelation function has a lot of coefficients with values larger than 5%, and for a chaotic orbit in the Veritas families, where the autocorrelation function with after 200 time lags, most of the correlation function, correlation factors lower than 5%. So we can apply this method to a well-known dynamical system like the non-analyzed Hamiltonian system. You can see above Poincare section of the Hamiltonian, this Hamiltonian use determined with the Sally chaos indicator. And below you can see the application with the new chaos method, the chaos indicator SFI. We are able to identify regular orbits, periodic orbits, and chaotic orbits that are found with other methods as well. So ACFI seems that might be working. So we can apply it to small body dynamics, which is the goal of our group. And we applied it to the Veritas families, asteroid region, Kuiper belt objects, and the Phocea asteroid family in the Malincrane region of the asteroid belt. So why it could be useful? It could be useful because it's essentially blind to the effect of stochastic events like cause encounter with massive bodies. So if you're interested in an indicator that only detect the effect of resonance overlapping, CFI could provide information without being contaminated by other effects of chaos like cause encounter with massive body of planets. So this is a work that we submitted to celestial mechanics, which is currently under review. So it has been talked before about time series analysis, and this is a very exciting branch of machine learning. So these have been, I will talk about a somewhat simple method for time series analysis, which are the Arima model, which are autoregressive integrated moving average models, which have been developed more than 20 years ago to predict the stock price behavior. So you can see in the figure how the stock price goes as a function of time, and the red curve is the prediction of Arima model for this time series. In astronomy, have been used to predict coronal index solar cycles, variable starlight curves, among other applications. So what are autoregressive Arima model? You have an autoregressive part, which connect current values of the time series to pass 1 to the relation Xt di, Xt equal A1, Xt minus 1, minus A2, Xt minus 2, minus plus AP, Xt minus P plus epsilon t. Where epsilon t is a normally distributed error with zero mean and constant variance. And P is the process order, so how many time lags you are taking in the model. And this is a free parameter of the Arima model. You have a moving average process where current values of the time series depend on recent error or shocks via the relationship epsilon dp plus b1 epsilon t minus 1 plus b2 epsilon t minus 2 up to b key epsilon t minus k. Epsilon t is the error term for the term, and the coefficient bi quantify the response to the previous shock up to order k. So you have, if you join the two models together, you have an Arima model, which has operates under the assumption that the series that you're studying has to be stationary with constant mean and variance. A series that is not stationary can be transformed into a stationary one by taking the difference of all elements with the previous series. So if the new series is not stationary, a new different series can be computed from the order one different series and then checked again for stationary. The process can be then repeated until stationarity is achieved. So you have an order of the series differentiation by which this stationarity is achieved, and this is the third parameter of an Arima PDK model. So how do you determine the coefficient and the free parameter? You are using one of the methods most commonly used in machine learning, which is the Box Junctions Approach. You start by exploring an exploratory analysis of your data, which is always a very good idea. And then you perform a parameter estimation using in some cases, automatic code like PM-Arima, which is a Python library for the use, very commonly used for time series detection. So you can detect the P, D, and K order of the model and the coefficient automatically. And you can perform diagnostic checking by determining a metric which is adequate for your problem. If the model is adequate, you go to the part of forecasting. If the model is not adequate, you go back to the part of parameter estimation. So there are several applications of Arima models, and there are also more advanced models that also involve seasonal effects, but I'm not going to talk about this Arima model. An application that we are trying to perform now is fitting the asteroid brightness of asteroids. So it has been known for more than a century that asteroid brightness is not constant, but present time variations that depend on asteroid shapes, albedo, rotation period, and other factors. The first asteroid for which this was observed was asteroid Eros, which is one of the closest to Earth. So Arima models are able to fit the light curve shapes with an error of less than 1%, even for very complex shapes. And you can see here there are one light curve for asteroid Ariane 43, and the pink area represents the interval of confidence for the Arima model for this light curve. So this could be an application, and we are currently studying if the classification of the asteroid light curve can be classified using Arima models. So the last part of my talk is going to be about deep learning. I'm very grateful to the previous speaker for introducing a lot of necessary concept for this talk. So deep learning is a part of a broader family of machine learning methods based on artificial neural network. Learning can be supervised, semi-supervised, or unsupervised. The artificial neural network is inspired by a network of neurons in biological systems. So deep neural network and switch a neural network with multiple layers between the input and output layers. There are different types of neural network, but they always consist of the same components: neurons, synapses, weights, biases, and function. I will not go too much detail into that, also because of the previous talks, but these components work similarly to the human brain. It can be trained like any other machine learning algorithm. So they are available in Python using the Keras and TensorFlow packages. And as previously discussed, they work extremely well with graphical processing unit or GPUs. So this is why they are very popular in these days. So as I said before, the main goal of our work is to apply machine learning to a problem of astrodynamics. So here are some recent applications of deep learning in astronomy. They have been used very, very recently to predict the stability of asteroids. There is a work by Liu et al. That uses artificial neural network to fit data obtained from the integration of more than 150,000 particles. So you can predict, you can make a stability map of these particles, and then you can predict the status of a new asteroid based on the result of this map. And here you can see the result in AI semi-major axis centricity diagram. Red regions represent the most stable regions, so they're time scale comparable with the solar system. Then you have semi-stable region, and then unstable region shown in black. So it's really not related to dynamics, but I think it's interesting for people that are working on asteroids. Neural network can be used to automatically classify asteroids into taxonomic spectral classes. So each asteroid has a spectral class depending on the time of the reflectance spectrum that we receive from here, from reflected light from the sun. And recently, we have neural network have been used to classify asteroids into different spectral classes using the MASB classification method and using simulating AI observations. So as soon as this data will be available, we should be next year will be automatically possible to classify more than 300,000 asteroids, which is a very interesting, promising result. So as told to discuss in the previous talk, deep learning can be used. It's one of the most common applications for image recognition. There has been a paper in this year for automatic identification of the comets in image of the Zwicky Transient Facility Observatory. And this is a freely available software which applies an efficient database architecture is capable to find comets in single images in near real time. So there has been the first comet that have been identified by artificial intelligence, which is comet 2022. And they recovered a comet that was discovered in 2016, but has been recovered this year. And finally, we use in our group deep learning for automatic recognition of images of asteroid resonant argument. We were interested in studying the resonant argument of asteroids in the 1 to 2 mean motion resonance with Mars. You can see here in the figure 3 kinds of type of behavior. You can have a circulation of resonant argument. If the argument goes to 0, 360, this will be the first image. You can have libration if the argument oscillates around 0. And you can have asteroids that switch from oscillation, circulation and libration, like, for instance, in the figure number 8, or figure number 33 here. So traditionally, classification of asteroid resonant argument is done by visually observing the result of numerical simulation of resonant arguments. Here we tried to apply deep learning to automatize the process, and we were able to classify about 4,000 objects that are in the mid-motion resonance, 1 to 2 mid-motion resonance with Mars. And this is a paper that we recently published in Monthly Notice. Well, I think that I'm going to finish a bit earlier than expected. So to summarize, machine learning in astronomy is a very new field of research. While I discussed that machine learning itself can be dated to the 50s, applications are very recent. Most of the papers that we have seen are in the last 5 to 10 years. It shows great potential with many new research papers published with applications supervised, unsupervised, and deep learning in astronomy. And a promising future awaits people who are willing to make the effort to learn these new methods. Thank you very much for your attention. And more information can be obtained from our research group site, the MASB site. Or if you're interested in some of the activity of the group, you can send an email at the dedicated email address here. Thank you.
So thank you very much for this very interesting talk. So are there any questions now from the audience?
Yeah, I have a couple of them, Christoph.
Yes, please.
One is, sorry, I'm hearing myself with delay. Now, when you say you recognize images from time series, what do you mean? That you transform the time series into an image?
No, what are you referring to? The result of the Arima model or to the
No, one of the late slides.